everyone. Hope you're having a good day. I'm going to lead you through section 1.8, where we're going to look at inverse functions. This is something we actually did back in Algebra 2, so it's been a minute. I bet we don't remember a whole lot about it. But let's jump into it. So up at the top here, this is how we're going to check to see if something is an inverse. So again, very wordy. Let's figure out what exactly we need to focus on. So what we need to check is we need to take two functions and take their compositions. This is what we did back in 1.7, where I'll take one function, g of x, and sub it in for x in the f of x equation. If they equal x, that means that we have an inverse function. Now, similarly, we also need to check the opposite compositions. If I then take f of x and replace it with x and g, we also get x. If both of those are true, then we have an inverse function. Okay, another important piece that we have up here, the function g is the inverse of the function f. And here's our notation where we see f of -1. And it reads f inverse. Okay, you could also say f of -1. So f, or f of its inverse, should always equal x. Okay, that's basically just showing this, that if we take a composition of an inverse with its original function, it should always give us x. So let's see what that looks like, because without an example, just a bunch of words that don't mean a whole lot. So with compositions, remember what we're doing is we're taking one function, let's call it f of x, and we're going to compose it with g of x. Now, I like to use colors because it really illustrates what's going on here. So the first thing we need to do is we need to see if I take f and compose it with g of x, does it end with x? So basically what this means is we're going to take g of x and we're going to sub it in for f. So what I like to think about is I go, okay, what does g of x equal? It equals x minus 2 divided by 3. So instead of me thinking about f of g of x, I actually want to think about f of what g of x equals, which is x minus 2 divided by 3. So what this means is in my f equation, everything's going to stay the same. So I'm going to write down 3. But the x, we're going to take out of here. I'm going to throw it out. I'm going to replace it with what I have here in green, which is equal to g of x. But right now, before I do that, this is literally just f of x. That x has been removed. I created a bunch of space. There's something new to come in, and that something new is what g of x equals, which is x minus 2 divided by 3. And now we just need to simplify. So there's a couple ways to go about doing this. If I read this out loud, it says 3 times x minus 2 divided by 3. So yes, the multiplying by 3 and then dividing by 3 undo each other. If you want to distribute, that's okay too. In fact, I would guess that's what most of us would do. If I distribute, I'm really distributing just to the top because the denominator is 1. So I'm really multiplying 1 by 3 in my denominator, and then 3 times x minus 2. Which is 3x minus 6 divided by 3 plus 2. If I'm dividing 3x minus 6 divided by 3, both of those terms are getting divided by 3. And sure enough, right, they divide out. And I didn't really need to do that because the multiplying by 3 and dividing by 3 did undo each other. So once I divide, 3 divided by 3 is x, 6 minus 3, or excuse me, 6 divided by 3 is 2. And there's a negative in front, so that's a -2. And plus 2, and we end with x. That's what we want. Okay, that confirms so far that we think these are inverses. But now I need to do the opposite, and I need to check if I compose g with f of x, we also end with x. So same idea. This time, instead of f of x, I'm going to write in what it equals, which is 3x plus 2. So I'm going to copy down the g function, except for that x used to be. I'm going to leave some space there. Now I'm going to fill in with what f of x equals, which is that 3x plus 2. And it's just good habit to always put that in parentheses. Lots of times, like in this case, they don't do anything. But if there are other operations happening to that original x, those parentheses make sure we keep track of our order of operations. So since they don't do anything, I have a plus 2 and a minus 2. Those cancel out, giving us 3x divided by 3, where the 3's divide out, and we end with x. So we can now confirm that these two are inverses of one another. Now, Could we have seen this before actually composing each function? Yes, right? We can kind of look at the two equations and see, do I see undoing operations? Like plus 2 and minus 2, they're probably going to undo each other. Multiplying by 3, dividing by 3, probably going to undo each other. So we can find these inverses, or at least get an idea as to are they inverses or not, just at a quick glance. But we still need to confirm by taking the combinations. Okay, so that's one way to verify if two equations are inverses. Now we're going to actually work on finding the inverses. So this is something we did in almost every unit back in Algebra 2, actually, where we found inverses of all functions. So here's how we're going to go about doing this. This is a step-by-step for what we need to do. We're going to first replace f of x with y. Remember, f of x is always equal to y. So we want to bring that y back in this case. And what we're going to do is we're going to interchange or switch. That's what interchange means, is to switch x and y. That literally means an equation where the y used to be, I'm going to put an x there. Where the x used to be, we're going to put a y there. And then we need to solve for y. That's the really important piece here, meaning get y by itself. If this equation does not define y as a function of x, the function of f does not have an inverse of function and its procedure ends. Don't worry about this here. We'll kind of point it out as we go. Okay, really we need to focus on just solve for y. And once we're done, we want to make sure we write it in the correct notation, where we're saying f of -1 or f inverse of x is whatever we find for the inverse. So let's take those steps and put them to use. So step 1 is instead of f of x equals 7x minus 5, it's to be y equals 7x minus 5. Once we have the y in there, I'm going to switch where the x and y are located. So now this is x equals 7y minus 5. So literally just changing the position of the two. And what that's signaling is our original domain is becoming the range, and the original range is becoming the domain. That's what inverses are, where we switch the domain and ranges. And we're going to actually do an exercise at the end of these notes with that. So now I need to get y by itself. To get y by itself, we need to add 5 first. After adding 5, I have x plus 5 equals 7y. Then to get y by itself, we need to divide by 7. So x plus 5 divided by 7 equals y. Know that we can write this in 2 ways, and I'm going to actually just flip it around so that we have y equals, instead of x plus 5 divided by 7 equals y. So I could also write this as x divided by 7 plus 5 divided by 7. Either way is acceptable. I just want us to know when we are dividing multiple terms by 7, each individual term is getting that divided by 7. Okay, and this is our inverse. And that's all we're doing here. Switch x and y and solve. Now let's look at 2 other inverses based on different functions. And when you get to the practice, you're going to have similar examples for you to practice on your own. And the last thing that I forgot to do up here, let's go back and fix this. This right here does not signal that it's a inverse yet. So we do that last step of writing in the correct notation of f -1, which is f inverse, equal to we just found. Or we could have wrote it as x plus 5 divided by 7. All right, so this is really what we're looking for. We want to make sure we bring in the correct notation. So let's try one here. Again, I'm going to change f of x to be y. And then just like before, I'm going to switch the location of the x and the y. There's now x equals y cubed plus 1. And we need to get y by itself. So -1. Don't want to get rid of the cubing yet. This is x minus 1 equals y cubed. And to undo cubing something, we need to take its cube root. The cube root and cubing cancel each other out, leaving us with the cube root of x minus 1 equals y, which is our inverse function. Let's just go ahead and write it in the correct notation. Inverse of x equals the cube root of x minus 1. Okay, so these are just basic equations. They do get a little more complicated as we add in more operations. But the key is switch x and y and simplify. All right, let's do one more of these where we have a rational function fractions can be scary sometimes, but you're going to see it actually isn't too bad. So y equals 5 divided by x plus 4. Let's switch x and y. So it's x equals 5 divided by y plus 4. Now, we have this dividing by y. Before we want to handle that, let's first minus 4 and get this whole 5 divided by y by itself. So I have x minus 4 equals 5 divided by y. And I'm like, you know what? I don't really know what to do with this. If we read it out loud and say 5 divided by y, what we actually want to do is multiply by y. By multiplying by y, we are undo the dividing by y, and I have to multiply both sides. When I multiply this left side, though, it's y times this whole thing. So I like to add in parentheses here so that I know that I have y times that whole expression of x minus 4, which now equals 5. And so now I'm like, okay, I got rid of the fraction, but I have y and then parentheses x minus 4. Remember that there's multiplication here. This is y times x minus 4. So to get y by itself, I can undo the multiplying by x minus 4 by dividing by x minus 4. Right? Anything divided by itself equals 1, so they divide out. And we get y equals 5 divided by x minus 4. I'm writing in the correct notation. We have found the inverse. Okay, so when we see fractions, don't panic. Always read them out loud and make sure you're using the word divided. And you want to ask yourself, how do you undo the division? By multiplying. Okay, and then if we have multiplication, we can undo that by dividing. So you're going to have 3 similar examples like this in your own practice. So you can refer back to these as you're doing your own examples. But I'd encourage you to try it before or on your own before taking a look at these. So write these down and see if you can do them by yourself. Okay, let's do a couple more things, and then now we'll wrap up the notes for this lesson. One thing we want to be able to do when we are trying to find inverses, just like we did on the previous page, I want to know, especially if I can visualize the graph, is will the inverse be a function? And we can check this by taking the horizontal line test. This works just like the vertical line test, except we're going to apply a horizontal line. So what this means is that if I draw a horizontal line anywhere on the graph, we only want it to intersect once. If it intersects once, then we can say, yes, the inverse will be a function. And now, when I get to a quadratic, okay, or a parabola here, when I draw a horizontal line, it intersects twice. So if I'm looking at this graph on its own, this is a function that passes the vertical line test. But the inverse, okay, or the horizontal line test is a way for us to check if the inverse will be a function. So what this is saying is that for when y is, let's call this 3, I'm getting 2 x values. So when we find the inverse and the x's become the y's and the y's become the x's, now it's not going to be a function. In fact, this graph of the inverse looks like this. It's an upside down parabola or a sideways parabola, and that doesn't pass the vertical line test. So the horizontal line test is a way for us to check if the inverse is a function or not. So here we're going to say inverse, not a function. And the reason it does not pass the horizontal line test. Okay, so here's our definition. A function f has an inverse that is f of or f's inverse if there is no horizontal line that intersects the graph of the function at more than one point. Okay, so here, if I draw a horizontal line, actually this one, we're getting 3 different x's for 1 y. So inverse, not a function, which is a problem. Okay, and then lastly, this one, no matter where I draw that horizontal line, it's going to only intersect once. So in this case, the inverse is a function. Okay, so why did we have to do that? Well, when we start looking at equations that are functions, but their inverses are not, we actually need to restrict their domain. So what does that look like? It says find the inverse of f of x equals x squared minus 1 and graph f and f of -1 in the same rectangular coordinate system. Let's first graph f of x. And so if I am graphing f of x, remember when in doubt, let's tee it up. Now I'm going to find, let's do -2, -1, 0, 1, and 2. So I'm going to plug these in. -2 squared is 4. 4 minus 1 is 3. -1 squared is 1. 1 minus 1 is 0. 0 squared is 0. 0 minus 1 is -1. 1 squared is the same thing as -1 squared, so it's 0. 2 is going to give us 3 again. 2 squared is 4. 4 minus 1 is 3. All right, so I can plot these values where I have -2 and 3. -1, 0, 0, -1, 1, 0, and 2, 3. Remember that when we connect points, there are arrows at the end. Okay, that's a real important thing. And now this does not pass the horizontal line test. So what we need to do is restrict its domain. That's what this is saying. So we want to graph when if x is greater than or equal to 0. What does that mean? That means x is positive. So when we are dealing with the inverse, I don't want these x's. So we can essentially get rid of all those negative x's. So we can essentially get rid of this side where the x's are negative. And now we have f of x, which is a function, and it is also now 1-to-1, right? The right side of this branch passes the horizontal line test. So by restricting the domain, we are allowing for f of x to be a function, but also its inverse, f -1, to also be a function. And so now we just need to graph the inverse. So how do I graph the inverse? I have x, I have f -1 of x. And so our original x's become the y's, and the original y's become the x's. Now again, I'm only going to take the values for where x was positive. So that's 0, 1, and 2. Those are going to be the new y's, 0, 1, and 2. That row and over there. And then -1, 0, and 3 are the new x's. I'll do this in a different color. So when I plot this, -1, 0. Yeah, put it cross that out. Right there in purple. It's kind of hard to see. 0, 1 is up 1 there. And then 3, 2 is right at 1, 2, 3, 1, 2. Sure enough, that's a square root function. Okay, let's make sure that we see this when we find the inverse. Okay, because we've graphed both. This is f of -1 of x. And this is f of x. So let's confirm that everything we did here worked out correctly by finding this inverse. By y equals x squared minus 1. I'm going to switch x and y. I'm going to solve for y, adding 1, so I get x plus 1 is y squared, square root. Y equals the square root of x plus 1. So the inverse here is f -1 of x equals square root of x plus 1. Now, we don't need to do this, but just to be safe, let's make sure that if I plug in these x's, I get these y's, and so we can confirm that by switching those x's and y's, that's a valid thing we can do. So I've got -1, 0, and 3. Let's see what happens. -1 plus 1 is 0. The square root of 0 is 0. Hey, that matches there. 0, 0 plus 1 is 1, and the square root of 1 is 1. Hey. And then if x is 3, 3 plus 1 is 4, and the square root of 4 is 2. Sure enough, the exact same thing. All right, so yes, there's a lot going on when we need to restrict the domain. We only need to restrict it if our function is not 1-to-1, meaning it does not pass the horizontal line test. If it doesn't pass the horizontal line test, we'll always restrict the domain to just be the x values that are bigger than 0. All right, thanks so much for watching. Make sure you complete the practice that follows. Those examples are going to be just like the examples we worked on these notes here. Have a great day, everyone. Thanks for watching.